Right. Well, good afternoon, everybody, and welcome to our AAPG Petroleum Structure and Geomechanics Division webinar. We have Jeffery Bader with us today. And before we get to that, I just have a very quick announcement. We are going to have our PSGD annual meeting in kind of in accordance with image. It's going to be Tuesday, August 27th. From 6 to 10 p.m. It's going to be at the Marriott Hotel in Houston. And the Marriott is one of the hotels kind of attached to the big exhibition hall. You don't need to be registered for image to attend. You can just park and come into the hotel and find us. I'll send a few more email reminders before then, but I hope to see some of you all then. And we also have sponsorships available for that group. AAPG is helping us with the room and the AV equipment. But if we want some food and drinks, then we got to get some good sponsorships. So we want to make it a fun time. So look for more emails and information on that, as well as our LinkedIn page as well. All right. And next up, we have Jeff Bader. He's going to be talking about wrench fault tectonic maps in the eastern Montana. And Jeff Bader has been a geologist for nearly 45 years and is a professional geologist in Wyoming. He has a BA in geology from the University of Colorado and an MS in petroleum geology from San Jose State University. He spent the first 8 years of his career at the USGS branch of the petroleum geology. He then was a consultant for more than 20 years, working for numerous firms. He spent the last 8 years of his working career serving the North Dakota Geological Survey, where he was director of the Wilson M. Lard Core and Sample Library for 5 years. In September of 2022, Jeff decided to semi-retire so he could focus on his research specific geological areas of interest from his home in Mexico, where he started Bader Enterprises. This research includes cratonic origins and development and resulting influences on the Phanerozoic, tectonic, structural, stratigraphic, and sedimentological evolution of sedimentary basins. Jeff's most recent work since semi-retiring has centered on analysis of potential Precambrian anisotropies and their role in crustal inheritance during Laramide orogenies in the North American Cordilleran foreland of Montana, Wyoming, and Colorado. Jeff has authored over 50 publications on these topics, mostly in the Rocky Mountain region. And I asked Jeff to give a webinar a couple years ago, so I'm really excited to have him here today. His work was extremely beneficial for me when I was working the Rocky Mountains and looking at kind of Laramide deformation and the impact of structural inheritance from past events. So I'm really excited to hear what he's got today. And Jeff, I will now pass it on to you. If you guys have questions, there is a little Q&A box. Feel free to type those in. You're also welcome to use the chat, but for specific questions, that Q&A box is really helpful. So on to you, Jeff. Thanks, guys.
Okay, thank you, Molly, for the introduction and the invitation to come and share my work today. Today's talk is going to be kind of a compilation talk looking at the major work I've done over the last 15 years or so. So there may be a little bit of repetition for any of you who have followed my work over that time, perhaps seen a couple of talks and figures from journals and the whatnot. And so just bear with me, because that'll only be about the third part of the talk. And then the rest of it will be focusing on looking at this wrench fault tectonic map that I'm working at on right now for eastern Montana. And hopefully we'll get wrap it up. My goal is to finish it by the end of the year, but it's still a work in progress. And so the review, I think, will be important, certainly for people who are not familiar with my work or critical. And 15 years is a long time. And so if you are familiar, I think a little background review will be good as well. So also in the last couple of years, since I moved down here to Mexico, I've been working on looking at lineaments in the basement chord uplifts and arches in the Rocky Mountains, along with to go with my previous work, and maybe to try to at least test that work. That main work, as Molly said, looked at Precambrian anisotropies in Wyoming, as well as up into eastern Montana, and the role that those anisotropies may have played during crustal inheritance during Laramide orogenesis. And then, as I said, in the last couple of years, I've been looking at these lineaments in the cores of these same uplifts and arches. Put together a paper that is also hopefully going to get out sooner than maybe at the end of the summer, that I hope can shed some more light or test my working hypothesis. And so the background slide that I show here is from the south to central Beartooth Mountains, just barely into Montana from Wyoming. And the thing I want you to note here, I'm not going to talk about the lineaments too much today. I'll touch on them, but this is a pretty cool slide. And I want you to note this. You can see the west-northwest striking, which are the dominant lineaments. You also see northwest striking, as well as northeast striking, northeast striking lineaments. So three directions there of potential anisotropy. And if you notice down here, the shape that's made by the lineaments, you can see my red dot down here that I'm using as my pointer. It's a parallelogram or a rhomb shape, as you see. And at this scale, this always captures my attention. We're always looking at about from the bottom part of the rhomb from corner to corner is about 3 miles or 5 kilometers. So this is a Google Earth image. This is Otter Lake right here. But as I said, this shape is very important to me, especially at this scale. And so I hope I can show you how important it is to today's talk. Also, I want you to note that these lakes that I mentioned there, Otter Lake, and if you look all around the background image, the lakes are concentrated along these lineaments. So it's clearly the lineaments are controlling the hydrology in this area and the fluid flow. And so I think that's probably important to at least a few of you who deal with fluid flow on a daily basis. So let's go ahead and get started. Whoops, sorry about that. Oh, there we go. Sorry about that. So I bet you didn't think that you're going to see Hawaii on my first slide here, but here we've got it. This is going back about 13 years or so ago. And at that time, I worked in downtown Honolulu and lived in Honolulu as well. And that's when I was doing consulting work. I had an office on the 10th floor here in downtown. You can see right here. So from there, had a beautiful view of Waikiki over here off to the east, and then also Diamond Head, which is way over here. And I had a corner office, at least for a little while in that job. And so I could just turn around and I could see the Ko'olau Mountains off to the north. And so while I was eating my lunch during my breaks, when I should have probably been admiring this beautiful view or getting outside and enjoying the beautiful hot Hawaii weather. Instead, I gazed at my wall and I looked at this image. And so many of you will recognize this as a Landsat image of Wyoming. And the thing that always fascinated me by this image was, again, a rhomb shape right smack dab in the middle of the state. And it's made by the Wind River Basin, the Shirley Basin, as well as the Sweetwater Uplift. And so this intrigued me from the days I started at the USGS some 40 years ago, or even close to 45 years ago now. And so it still does intrigue me, but I think I know a little bit more about it. But my first thought when I was in Hawaii is, how do you do this? How does this form? Is this a random feature, or geologically, is it something more fundamental? And so it's something that I decided to look into. And I was in Hawaii. I just finished a paper along the southern part of the state, along the Cherokee Ridge, which was my master's thesis area. I published that in Rocky Mountain Geology, and also did another paper for northwestern Colorado, furthest south, on the Douglas Creek Arch. So I was looking for things to do, so I decided to follow my nose. And I thought, okay, well, let me look more to see if I see this shape. Is it there in other places? So I didn't have to go very far. I went down to the southwest into the greater Green River Basin, which you see here, coming into northwestern Colorado, and Craig is right here. And so with the greater Green River Basin, you can also see a rhomb shape. And so I mentioned, I'm going to kind of beat a dead horse here. But anyway, it's not quite as significant as what we saw in there in central Wyoming, but indeed a rhomb shape. So I thought I might be maybe onto something. Maybe we're seeing something that is not so random. And then so I decided we're looking at perhaps I'll take you back to your early days in mineralogy and looking at something more fundamental. And I thought that a calcite crystal with its rhomb shape would be something similar that I could show you its fundamental origin. But back in mineralogy, when we had our little box of minerals and we were trying to identify these minerals, we might have 20 or so in a box, and they all had the same shape. Some were big, some were little, some perhaps were maybe even broken or fractured, and so we really couldn't see this beautiful euhedral symmetry. And so a geologist kind of knows what's going on here, but anybody could look in that box, and you don't have to be a scientist, have much experience or whatnot, because you look in there and you say, something's going on here, and something's going on to cause this to be orderly and systematic. It has fundamental origins at the ionic scale, so we may not even be able to see it as with calcite and the naked eye. And as I said, you can maybe break these up, they're shattered or whatever, which would disguise that original symmetry. But the symmetry is there. And what I think we need to do, in my opinion, and this is what my work is really based on, is looking at this shape at larger scales. Does it really pertain to continental or plate tectonic scales? I know all of you, or many of you, look at this shape. It's not anything new. Other geologists have seen this shape at the larger scale, but they haven't really put together its origins. And hopefully I'm doing that with my present work. But at the outcrop scale, you see this all the time. We see it weekly with Molly's stuff on LinkedIn. But like I say, is it applicable to those larger environments in the plate tectonic scale? So I'm in Hawaii and I have a GIS available. So I thought I'm going to go up into Montana, another part of the Wyoming Craton, and I'm going to see if I can see what's going on up there. And I found out the Montana Bureau had some beautiful maps, 100K maps, everything mapped. It was all available digitally. So I thought, well, there's wrench faults up there. I know there are wrench faults. There's not a lot written about them, but they've been documented over the last century or so. And so I thought, I'm going to take these maps and bring them into ArcGIS and see if I can make a wrench fault tectonic map. So that's where wrench fault tectonic map 1 started. And we're going to talk about number 2 later on. But anyway, so I made this poster, and it's got some Google images from these various spots, and then the map showing the features from those spots, and then a little line going into the map. And I presented this in Utah at a GSA meeting. And that was really good, but it didn't get much attention unless you went to that meeting, and that was kind of an afterthought after that. But while I was doing this map, I came upon the deadly ROM shape. Okay, we go down into the Pryor Mountains, and I do know this is the state boundary, but if you come down here into Wyoming a little bit, you will realize that this is it's kind of an oblong ROM, but there's a big fault here that runs roughly east-west, giving this ROM shape again. And we see it from the fault zones that I mapped in that first map. And so, you know, pretty soon I started seeing these things under my bed, like a Stephen King novel. And so now you can imagine what I'm like, at least at night when it's dark. But anyway, so I thought, okay, I'm seeing this in several places. And like the calcite crystals, I'm starting to think, well, this has got to be some sort of fundamental origin for these. I got to do more. So I decided to write a paper because I was seeing similar things in Montana and both Wyoming. And so I included the whole Wyoming craton and submitted probably 2014. And that paper was sent back rather promptly. It wasn't in perfect shape, but I got some good reviews. And one of the reviewers said, you should break these up into two areas. Do a paper on Wyoming and do a paper on Montana. And so I thought, you know, that's a good idea. And I got Montana, Wyoming on the brain, which caused a little problem that we'll see here in a little bit. But so I started with Wyoming, and I put together a paper there that was published in Lithosphere. Excuse me there. And this is a figure from that paper. And so my premise there was, if you look at the yellow here, this would be what I call the proto-Wyoming craton. The actual craton boundary now is the purple, and we'll talk about that here in a little bit. So we've got the full state of Wyoming. You've got this yellow, which has been defined as the part of the craton where rocks are greater than 3 billion years old. And so this was established at about 3 billion years. It does extend off a little bit more into the state of kind of the western side of Montana and a little bit into Idaho, but not very much. Okay, so this is kind of a almost rectangular, long, very narrow protocraton, and my work suggested that we had subduction going on at the present zone of the Piney Creek thrust, as well as the Wind River thrust. This has been shown by the group at the University of Wyoming, Frost and others, that this is a pretty long-lived active continental margin back in the Precambrian at about 2.9 to 2.6. So this works out with my idea. I propose there are subduction zones here, and with that subduction, you're going to have convergence, maybe overlapping at each of these times, probably earlier to the northeast here than to the southwest. But you're basically squashing this rectangular craton, and I believe we see that expressed now in form of conjugate shears within the craton interior basement. And so we have east-west striking. That would be the Tensleep fault, which is exposed in the basement, and I believe extends out into the Bighorn Basin we'll talk about. And then the North Owl Creek fault, which I believe also extends even further than I show on this figure, and we'll talk about. So you've got those definite zones of weakness, the subduction zone itself, and perhaps when you go inboard, you're going to have ductile shear zones, brittle shear zones, as well as frontal thrusts along this northwest trend. So that's one zone shown in green. And then you have the conjugate shear. So I looked at fabrics across this area as represented by these Rhodes diagrams to try to show that indeed these features were formed in the Precambrian and then were reactivated during Laramide simple shear. So again, the craton boundary in the pink, and study area that we're going to talk about today is further north, but here we can see Wyoming up into a little bit into Montana, and you can see the Precambrian exposed units here very well in the orange. And so we have those faults, the west-northwest trending striking. This is Tensleep, North Owl Creek. You get down in here. These are the prominent faults. And so you have those old subduction zones, which now are major reverse faults. They're reactivated. The drivers in this area, I believe, are these left lateral strike slip zones that you see through coming through here in Wyoming. And I'm going to show you more that I found just as a result of doing this, putting this talk together and putting the map together. Okay, you also see dextral oblique slip faults along with the sinistral oblique slip fault, but they're don't play quite the major role that we see, and I'll show you why in a little bit. But anyway, so when you get in the Laramide, you get compression from the north 40 east direction, and that's going to push on these synthetic strike slip faults and cause them to move in the basement and cause deformation in the sedimentary cover throughout this area. So at that point, I got that done, and I decided, okay, I'm going to go back to Montana and see what I can do there. So I did that. I put together a little paper, and so we're going to talk mainly about Montana as we go forward here. So let's first talk about the Laramide Belt. So the study area here now is shown, and again, we've got the Wyoming province in the tan here. So we're looking at the northern part of what I call the Wyoming province, as well as the north of the Laramide Belt, which is shown in blue here and shown in brown in the larger figure. And so we go back, if you look at Montana over here on the small figure, keep in mind that this isn't all of Montana. So the figure I made didn't go all the way up, probably should have went further north, just so you know. But anyway, so study area shown better here. And you can see that area is north of the Laramide Belt. So Laramide Belt in brown. I imagine most of you are familiar of this classic origin where we have 60 million years ago, a Farallon plate, shallow angle subduction. I think this is pretty well understood to be the reason why I have this deformation so far inland from the active continental margin at that time, creating the deformation that we see with these what appear to be random oriented uplifts and arches. And I do distinguish between the two, and I may be the only one, but they do, as we look, they do look pretty anastomosing, random, but I'm going to argue that they are anything but, and certainly in Wyoming and up into Montana. So again, during the talk, please keep in mind that principal horizontal stress during the Laramide was from the northeast. Okay. Now we'll move on to the central Montana uplift, which was the name I kind of gave this area, uplifted area from just north of the Beartooth uplift up to the northeastern part of the state. Not to be confused with the central Montana platform, as well as the central Montana trough. Work done by Lageson talks about the central Montana platform. And I do believe Bouquet, however it's pronounced, is doing work with the state of Montana, and she also calls this, I believe, the Central Montana uplift. So my Central Montana uplift, as we'll see, is pretty prominent when we look on isostatic gravity. Okay, so we are looking at the eastern part of the state, as you can see on the smaller figure. So it's a large area. We're looking about 2/3 of Montana. All right, so you can see the Williston Basin that you're all familiar with. North Dakota is off over here to the right. So the Cedar Creek Fault here is here. Powder River Basin, the northern part here in southern Montana, Pryor Mountains, as I mentioned, the Beartooth uplift, and then centrally within the central Montana uplift, you have some inner uplift basins, I guess, Bull Mountains Basin and the Crazy Mountains Basin. And then we also have these fault zones, Lake Basin Fault Zone, Cat Creek Fault Zone, and Nye Bowler Fault Zone, striking to the west-northwest, and then northeasternly striking fault zones, the Fromberg Zone down here by Billings, the Weldon Fault Zone, as well as the Brockton-Froid Fault Zone as you get to the northeastern part of the state. And so this is just the geologic map from the state with the structure shown on here that we're going to talk about today. So again, we'll start with talking about the west-northwest when we get to it, and then we'll talk about the northeasterly striking zones. So study objectives, straightforward. We'll go on to create the wrench fault tectonic map, the dose. Actually, I've learned my little bit of Spanish here. Classes, circuit structures are based on this simple shear model. Same thing I did for that first one. And then putting this map together, utilizing that beautiful data from the Montana Bureau into ArcGIS and then Illustrator. And you'll see the Illustrator later today. And then I want to publish this along with some of my recent work that'll go with the map. So you say, what's wrong with you, Jeff? Why would you want to do this not only once, but twice? And even though you don't live in Hawaii anymore, maybe you're bored. Oh, yeah, you live in Mexico. Well, call me crazy, but I love it. So previous work from many authors that I said over the last century, from Wilson to Hancock, have shown that there's a wrench fault complex in this area, but not a whole lot of work, and it hasn't just been expanded upon much. People just say it's there. We see these similar features exist elsewhere, especially down into Wyoming. And we're seeing, at least in my work, that maybe they're longer, bigger, wider, and go into these sedimentary basins and are beneath these basins more than we previously thought. And obviously, oil and gas, minerals exploration is going to go on for some time. I'll be gone before it's over. And now we have these new problems or things that we need to deal with, carbon capture, looking at geothermal energy, hydrogen, helium, etc. So these structures are important, and I believe they're very important, but they tend to be maybe not focused on so much in the literature or in exploration, at least as far as I can see. And they're looking more with the thrust tectonics in the Rockies. So let's look at some Laramide belt wrench fault zones. So this is kind of a similar map that you saw. You can see the Laramide belt and the Laramide basins in the light blue here. So I've done, and then you can see the states in the background, Montana up here, the Laramide belt extending all the way from Arizona, New Mexico, all the way up into, barely into southern Montana. And so I've shown, you can see left lateral in red and right lateral anithetic faults in the blue. And that's just what I believe these are in the basement. And we'll talk about that today, and formed in the Archean and in the Paleoproterozoic. And so Montana up here, I have now proposed, I mentioned I'd found some new ones. I'm proposing that up by Poplar Dome, we have the Poplar Dome wrench fault zone. And I'll say that 3 times real fast. Coming down in this area, what we just talked about, I'll talk about these fault zones as well. But first, let's go into Wyoming and look at a little work where I've done very recently and published some papers on to show you the extent of these features. Now, I do bring them all the way down into kind of central Colorado, central Utah, but these are the ones that I have most experience on. Okay, I've worked with these quite a bit. That doesn't mean there's nothing down here to the south. And I have some suspected zones. I didn't show them on here though, because I haven't done much with them. So keep that in mind, that that's why this is blank. So let's go up into north central Wyoming. So here's the Powder River Basin, Black Hills Arch, Bighorn Arch, Sweetwater uplift through here, the Wind River Arch, and the Owl Creek uplift. Laramie, or Casper, excuse me, is right here. And so we've got 3 fault zones, and 2 of them I wrote papers on for the mountain geologist. And I showed how these structures extend, I believe, border into the basins and were connected more than people believe below. And so the first one, or before, excuse me, was the Owl Creek fault zone, which now I have been told with personal correspondence based on my work, I believe that it extends at least into the Powder River Basin, and they are drilling some unconventional Cretaceous plays here utilizing my work. I believe it may go all the way to the Black Hills Arch, but I dashed it there. Also looking at the Casper Mountain Fault Zone, I put together a paper where I connected. These things are very linear. The Douglas Fault Zone going to the North Granite Mountains and even up into fault zones in the Wind River Arch that do show those same three directions of anisotropy that I mentioned on my the cover slide there with the lineaments up in the Beartooth Mountains. So you can connect these down into the basin. So I believe this fault extends quite significantly as well. Tinsley Fault, that'll be the next paper. As part of this work again, I found a nice map for USGS that shows this area. So I'm going to try to put a wrench fault tectonic map together and a paper for that. And that USGS map is, I think it's called the geologic map of the Powder River Basin and surrounding areas. And so it goes up into Montana as well. And we'll tie very nicely. But this Tinsley Fault Zone, I'm going to show a figure that will show what's going on in the basement, a structure map. So exciting things to come. But anyway, longer, and we'll see wider if we look at the Cat Creek Fault Zone when we get to Montana. So let's quickly review my previous Montana work. Isostatic gravity here of Montana. This is the entire state, and you can see here the scale, and we're going to look at gravity highs and gravity lows. So let's bring in some labeled stuff. Williston Basin, pretty easy to see here. Powder River Basin as well, and so you can see it's well defined. And now I'm going to talk about the Wyoming province. Okay, I am familiar that there is some recent work that maybe you're going to change these boundaries. I'm going with the old school boundary that has it off here to the northeast, goes up maybe a little bit even into Canada, comes down, winds around down into Idaho a little bit, and then goes down in through pretty much all of Wyoming. So as far as Montana is concerned, I like this isostatic gravity map and the things that it shows. And so I'm going to stick with it until somebody shows me otherwise. But I am familiar with previous work, most recently, that's showing that the Wyoming craton is smaller. And so maybe by up to a third to a half smaller. And this work, I'm not going to judge that work here, but like I said, I'm going to go with the old school. But since it seems to be changing, at least maybe on a yearly basis or monthly basis, perhaps a year or two from now, there won't be a Wyoming craton, and I'll shut up. But anyway, we're going to go with this boundary. So you can see the central Montana uplift here is pretty well defined. You can see these gravity highs from down here from the southwest up to the northeastern part of the state. So we'll talk about that in a little bit here. And because this boundary, I like this boundary because you can really see, we're going to talk about this, what I believe is a major crustal boundary, another major crustal boundary here. This would be the Great Falls Tectonic Zone through here. So it looks good. It looks different from the central Montana uplift. Yeah. Okay. I like to be able to look and see what I think I should see. And then the Medicine Hat block over here, severe fold and thrust belt. So let's go ahead and bring in those surface faults. These are faults from the Montana Barrow brought right in. And now you can see these left lateral, what I believe are synthetic strike slip zones, okay, from convergence that are formed in the Precambrian. And these faults here are going to be dextral strike slip faults striking to the northwest. And you can see they have a distinct arrangement that make them look at least like conjugate shear zones. Okay, and now the central Montana uplift is kind of taking a better shape here. Let's bring in those zones that we know are we see at the surface and have been discussed: Cat Creek, Lake Basin, and Nye Bowler that I believe have been reactivated during Laramide orogenesis, along with the Fromberg, Weldon, and Brockton-Froid zones off to the northeast. And now you're really seeing the central Montana uplift as this gravity high. It can't be ignored, in my opinion. And then you have the the Cedar Creek fault zone over here, which I believe is a major Proterozoic crustal boundary. And I'm showing the Nye Bowler through here. And I believe now that this is a crustal boundary, but as I'll talk about in the next slide, the Nye Bowler fooled me a little bit, but it still would be reactivated. The reason it fooled me because it has the same orientation pretty much as the Lake Basin and the Cat Creek fault zones. So anyway, Precambrian fabrics. So when I got into Wyoming, I thought, well, I should look at some Precambrian fabrics, just like I did for when I got into Montana, excuse me, just like I did for Wyoming. So I did find some, thinking that because these Cat Creek, Lake Basin, Nye Bowler zone, pretty close to what's in Montana. And like I said, I kind of got fooled by this. You should do the Montana and the Wyoming work separately. Because I believe now that the Nye Bowler fault zone is a different animal. I don't believe it formed. My working hypothesis is that convergence during the Paleoproterozoic did roughly the same thing that I talked about earlier in my lithosphere paper on the Proto-Wyoming craton, but the Nye Bowler zone would mark that boundary, okay? So anything south of the Nye Bowler zone should have been included in the Wyoming work, and it wasn't for this paper that I did for the Tobacco Root Geological Society. However, it does agree with what's in Wyoming, so that's a good thing there. But anyway, I digress a little bit, but it's important to you know that, important you to know that the convergence is from the northwest or northeast and was at the Cedar Creek Fault Zone from the northeast during the Paleoproterozoic that formed these basement zones of weakness that were reactivated in the Laramide. So it's a bit of a mouthful, but you'll see what I'm talking about here as we go forward. So I did have the lineaments, also working on those right now, as I mentioned. But as I said, now I've lost the Precambrian fabrics. And so the only thing I have left are surface fault zones, because further into central Montana, there's no Precambrian exposed, or not very little, so you can't get any fabric data. So all I have is these surface fault zones. So let's take a look at that very quickly. We'll look at the west-northwest and the northeast. So Cat Creek Fault Zone further to the north. So I've got a rose diagram here. For the west-northwest, I'm going to show the fault zone in a light gray. Okay, so this is the orientation of that fault zone that we see in map view. And you're going to see it on all three of the west-northwest as we saw on those maps. Okay, up here I show what I believe occurred in the Precambrian. So we have a pure shear of the stress coming from the northeast. I believe it's going to break those basement rocks that were there at the time along that Cedar Creek boundary, and you're going to get conjugate shears. Okay, you've got synthetic strike slip fault, anesthetic strike slip fault. Over here, I have the simple shear strain ellipse. This is what would happen then during Laramide orogeny, and you had the basement reactivated during Laramide stress from north 40 east roughly, reactivates these zones, and these are going to be the features you see in the sedimentary cover from that reactivation. Okay, so what we see in the Cat Creek at the surface are dominantly normal faults, as would be predicted by a left lateral buried basement fault shown here in gray. Okay, so it matches very nicely. Maybe we have a few subsidiary anesthetic faults as well in this area, but dominantly normal faults that we saw on the map. Okay, same thing with the Lake Basin. All right, same orientation of the zone and dominantly normal faults as predicted by the purple. But with Lake Basin, we also perhaps have some normal faults and maybe even some anesthetic faults as well. Then we move down. So this, as I said, forming from convergence in the Precambrian, you get conjugate shears, and then later during Laramide orogeny, you get the sedimentary cover disturbed to the surface, and we see patterns that we can see in the simple shear strain ellipse and reactivated as left lateral on those. Nye Bowler is a little different animal. I believe, as I said, I first thought it was due to convergence, but now I believe it's that major crustal boundary. So I don't show anything up here. However, it's in the same orientation as those two zones we just saw. So again, we're going to get the same thing. We see more of a potpourri here on these zones, but again, dominantly normal faults. But we'll see as well in a second, as I said, kind of a potpourri of simple shear subsidiary structures. Fromberg fault zone, these northeast fault zones then, all we see really are the trace of the basement fault at the surface. We don't really see too many subsidiary structures. So this is the Fromberg fault zone. Again, we would expect from convergence. These are going to be the ones to the northeast, shown here in blue. Pretty much a perfect match. And then reactivation during the Laramide, then we probably have some reverse faults and a few other on the Fromberg. We moved further to the north, that Weldon zone, only 10 here readings. And that's pretty much just defining, again, as I said, what the master fault is in the basement, defining that zone. There's not a whole lot of motion on these zones because we don't have too many subsidiary faults. And then we see the same thing for the Brockton-Froid. Its orientation is a little bit more towards the northeast. I'll explain that here in a little bit, but I believe it's due to offset from the Poplar Dome fault zone. So again, we get convergence. You're going to get development of these anisotropies shears. They'll be reactivated during the Laramide. So everything fits pretty well. And these are going to be right lateral strike slip faults or dextral. So methods one was to confirm the nature of these zones. And I said at gravity, I did that structural analysis, but I had to throw out now those fabrics. So I thought, well, what else can I do now that I'm down here in Mexico, have lots of time? Well, maybe more structural analysis. And that's when I thought of recreating this wrench fault tectonic map of eastern Montana. Methods then were to make the map. And as I mentioned, Montana Bureau data, ArcGIS, Adobe Illustrator, and then I'll be writing a paper that I hope to publish with some more analysis of what's going on. So let's quickly talk about the results. This is all in Montana again, the geologic map. See the fault zones here. So we're going to start down by the Pryor Mountains, southern part of the state. The Beartooth uplift over here, Billings about right in here. So we're now at the northwest part of the Pryor Mountains. This is what the map is going to look like. But I started putting together at 1 to 100. So I actually had to stitch these maps together. So we're looking at two maps here. This is the Billing 100K, Billings, and the Bridger 100K. So as you can see, I've shown the fault zones. I'm going to zoom in, on this a little bit. So don't worry too much, but in gray, you can see the fault zones. This is the Lake Basin, Fromberg, and the Nye Bowler. But this is only 2 of 54 100K maps. So I had to go to 1 to 500 to finish the rest of the map that you'll see more of, not completed, but more of in a second. Simplified the geology, so the explanation is going to be over here. I'll show a simple shear strain ellipse with various colors defining the different subsidiary structures that I just talked about, and we'll see more detail. And then the various faults in those different colors, folds as well. And as I mentioned in the light gray, we'll see those buried wrench fault zones. So now we're going to go zoom in on the area just on the western side of those Pryor Mountains. Zooming in here, we see the Nye Bowler fault zone itself. Okay, we put that in here based on the orientation of these other faults, okay? The other faults you see are color-coded based on the simple shear strain ellipse. So we have some anisotropic strike slip faults. These are going to be dextral faults in aqua. Purple are the normal faults. We see them, beautiful orientation and match rather nicely. Synthetic faults are roughly east-west. Synthetic faults east-west. These are going to be sinistral faults. Okay, so this is all from the Bureau. Nothing has changed. If there was a mistake or obvious mistake, I changed it. But this is their data, including down-thrown, strike slip arrows, etc. Neat thing to notice here, we see a normal fault here, as well as an anisotropic strike slip fault, 2 different colors. But this is mapped as the same fault. And this is interesting because of that change of strike. Will you see a dip slip over here, normal slip? And would you see dextral slip if you could visit this in the field? That's one thing I would look at if I could go. See same thing here with a synthetic and a P shear. So strain ellipse predicts this pretty well. So I said I used these faults and their orientation to identify where the Nye Bowler goes through and not vice versa. Most people would probably put it through here. It makes a nice lineament. These are synthetic strike slip faults in my interpretation. But if you did that, this would not work. And what I'm going to show next would also not work because the Nye Bowler has to curve through here to explain the prior mountains. So that's what we're going to go to next. We'll look at the, oh, excuse me, not yet. We'll get there in just a minute. We're going to look at the western side of the Powder River Basin, Sarpy Creek area, Ash Creek area. So here we've got the Sarpy Creek area. This is a paper in Mountain Geologist from some years ago in 1986. And what they did here is they did the same thing. So these are structure contours on top of one of the coals in the Fort Union Formation. I bought the strain ellipse in, Robinson and Barnum, who worked for the coal branch, had like 800 borings here. I actually worked with these people back when I was USGS, and they did a nice paper. And they showed these dominantly as normal faults in the shallow subsurface. They use that to identify where the Lake Basin fault zone goes through based on the fact that they saw the normal faults were down thrown to the southeast, north of this zone, and to the south of this zone, this other color, they were down thrown to the northwest. Okay, showing the orientation of that, normal faults dominantly, and that's what you would predict here, the master fault zone in red, and we can see it striking off to the northwest. Did the same for the Nye Bowler in the Ash Creek area. Ash Creek produces oil, or at least produced oil. I'm not going to get into the nitty-gritty of this one. Pretty much the same thing, and they use that to identify the approximate orientation. Maybe not give you exactly, but it gives you a good idea where that master fault goes through, which is kind of what I'm harping with this map that I'm putting together. Now let's go to the prior mountains. In the prior mountains, we have a what I believe is a restraining bend. So this is the Nye Bowler fault zone coming through here. Goes more east-west to the west and more east-west down here to the east. So there's a curve here. And in the terminology of Maclay and his group, this is a restraining bend. It curves so you get compression from either direction that causes a pop-up, or as Maclay's group would call a rhomboid sigmoidal uplift. So there's that rhomb shape again. And whoop, we bring in the sinistral strain ellipse, which I depend on. As you can see, if you have a strike slip fault in the basement at this orientation, you're going to get those synthetic strike slip faults, as I mentioned, anesthetic as well. Dominantly here, we're seeing thrust faults and some folds predicted to the northwest. Dominantly here more northwest, related just to the reverse faults that we see in the orientation. I think dominantly because we have this transpression from the east and the west. Okay, now we'll move on to some of the basins. If we go to, let me go back here, we're going to the north, to the Bull Mountains Basin. So this is between the Lake Basin fault zone and the Cat Creek fault zone, which is a wider zone that we'll see. We're looking at the Bull Mountains Basin. Again, in the terminology of Maclay and others, this is a, what I believe, a releasing step over between the Cat Creek fault zone, this wide fault zone, and the Lake Basin zone. So Billings is down here south of the map, and I drew the what's the releasing step over here as would have been done by Maclay and others in this wide zone. I just put this right in the middle of the Cat Creek zone because it is a wide fault zone, and the Lake Basin, the stepping zone. And when you do that, you get the step over and the development of what Maclay would call an elongate box graben pull apart. And that actually does take a rhomb shape as well. So we've got this basin dominantly forming, I believe, from strike slip tectonics during the Laramide, but we also have some thrust loading probably from the north. Okay, now we're going to go from that Bull Mountains Basin now to the southwest. We're going to look at the Crazy Mountains Basin, which is just north of the Beartooth Mountains. What I've done here is drawn two composite geologic maps for both Wyoming and Montana. And I'm going to try to take you through what happened late Cretaceous through early Paleocene. And so what we can see here, Crazy Mountains Basin is right in here. It's just north of the Beartooth uplift. What I've drawn here is what I think is probably a basin that formed, which would include the Bighorn Basin, because this really is one basin that's just separated by a high along the Nye Bowler fault zone. So this is all just hypothetical. This basin could have been any shape, but I drew it like this so I can show you how I thought this evolved from late Cretaceous when Johnson and others showed that the Crazy Mountain Basin formed. And so with that, we'll get into all of this through time. And again, the time is just approximate as well. Okay, so we get this forming in the late Cretaceous. You start getting sedimentation from the Helena salient dominantly into the Crazy Mountains Basin during the late Cretaceous. I don't want to forget, Crazy Mountain Basin has 30,000 feet of rock in it. So I don't think it's just thrust loading. Can that be minor, beginning at the beginning? And then by the early Paleocene development of the Beartooth Arch and the Bighorn Arch, you started putting sediments into the basin. And then you're probably going to get wrench faulting starting based on my working hypothesis. So I showed those wrench faults that you've seen earlier, and then I put some in here through ones that I know that are there already with the tin sleep coming through here, right through here, Owl Creek. But now I've shown 6 or 7 zones through this ellipse, okay? And if you have left lateral motion, which is what I'm proposing, through time, you got early Paleocene. By middle Paleocene, you start to narrow this thing down and it start to takes a reverse S shape. By late Paleocene, even more, okay? And again, this is just kind of approximate what would happen, okay? So you start to see, and this is due to the left lateral motion just moving this and deforming this previously formed basin. By early Eocene, it's taking the shape of its present day, and by the end of the Eocene, it has its present day shape that I show here in the light brown and the yellow boundary. And so this is all related to strike slip deformation, and in my opinion, and that's going to give us this reverse S shape that I call an S hook or a reverse S hook. This is the best developed in the Wyoming province, but across the Wyoming province, we see this in pretty much in some sort of form or shape across these basins, this S hook shape. Neat thing to see here, Nye Bowler fault zone is right here at the border. You go north, you have a basin. Lake Basin fault zone. Go north, you have a hook basin. Cat Creek fault zone. You go north, you have a hook basin. And now if I put the Poplar Dome fault zone up in here, I'm not showing it, but again, north of there, a hook basin. And this is what gives the Williston Basin the bear shape that we see on everybody's maps. So I'm seeing symmetry, lots of symmetry. So Laramide, Precambrian tectonics, I'm running out of time, so I probably won't show the map in Illustrator as I'm running down here on time. But in the beginning, we all know there was Billings. And so I'm going to do kind of a time stepwise to show you what I think is going on here to summarize. So you have the northern Wyoming province here by the end of the Archean was cratonized, okay? And that's been shown by other workers. So by 1.8 billion years ago, this was the northeastern boundary of the Wyoming province. And I show the late Archean, the proto-Nye Bowler fault zone down here. So at this time, the northern Wyoming province was, I believe, deformed by some sort of rigid indenter coming in from the northeast, converging, and I believe this was a crash zone. So what you have here is this zone, similar to the Himalayas back in that time. So we probably had Mount Everest type of mountains back then. A collision zone, so we're going to expect conjugate shears in 2 directions. But note, we only have 2 directions rather than what we saw in Wyoming, where we had 3 directions. And I believe that's because it's a collision zone and not a kind of standard subduction zone. But you couldn't predict this any better with the pure shear strain ellipse. You have strike slip off to the northeast, your anesthetic, and then your synthetic strike slip faults in red. off to the west, northwest. And so that again is my working hypothesis. Then you get Laramide orogenesis. And here you can see now why the anithetic faults probably haven't shown much reactivation, but we do see the surface trace of those faults, whereas the west-northwest faults, with this stress at that time, it's going to push right on them, and you're going to see them be the dominant west-northwest structures moved along with this Nye Bowler fault zone boundary. And that's where we see I bring the faults in, and you can see those normal faults that I showed evidence of from on all those maps that I showed along the lake basin as well as the Cat Creek zone. Boundary here is the Cedar Creek fault zone, showing it here. And then I bring in those strain ellipses, again, beating a dead horse. Those normal faults really can be seen, and that's the orientation that you would expect from simple shear on a left lateral buried basement fault. Okay, so summarizing that, I brought this isostatic gravity in from 1.8, bring in North Dakota and South Dakota, and you can see some beautiful gravities high. They're a little bit different color here, again, because I had to stitch these together. Williston Basin over here. So you've seen this part, central Montana uplift. So what happens is this comes in crashing. You get the conjugate shears. I apologize for the color. These are in green. So the synthetic faults are in green here, anithetic faults are in blue, but just was to be predicted. You've seen this already. And then simple shear during the Laramide orogenesis is going to reactivate these zones during the Laramide. And now look, we've got this big, what I believe is a volcanic, some sort of island arc that crashed in during Paleoproterozoic time. So it's a Proterozoic island arc that hits this and creates that major mountain building episode and deforms the northern part of the Wyoming province into sets of conjugate shears that are reactivated during the Laramide. So in conclusion, you get the development of these conjugate shears in the Precambrian, as I mentioned, collision boundary and pure shear, beginning of the Trans-Hudson. Reactivation, don't need to talk a whole lot that. I've kind of talked about it a lot. This is in basement involved deformation though. So I believe the northern extension of the Laramide belt should go all the way up into nearly, if not into southern Canada. And this is consistent with my work from my lithosphere paper. The thing I really want to preach though is this symmetry. And symmetry, I don't believe can be explained. And the lineament work that I'm doing is supporting this, in that it looks like if it was just a Laramide event, we would see these lineaments in the same orientations in the cores of these Laramide arches and uplifts, and we don't. So it suggests that in the Precambrian, we see these lineaments in different orientations based on different timings of these collisions and subduction zones. We would not see that if it was just Laramide, in my humble opinion. And it does give us insight into these zones, convergent episodes, and the assembly of Laurentia. And as I stated earlier, is most helpful for you guys in your exploration for oil and gas, etc. And with that, I'm going to say thank you. And I'm sorry I didn't quite get to the map itself in Illustrator. I don't know, Molly, do I have time to go into that or not?
Yeah, if you have a minute, I think
it'll be very quick. I'll just do it real quickly here. Here are my references, mainly. Thank the Montana Bureau, Reed, Robinson and Barnum, and then Wheel and his group. So I'm going to do a stop share for a second. I'll be right back.
Okay. Yeah, there's no questions in the Q&A box yet, so go ahead and feel free to pull that up. And in the meantime, we'll just say thank you. I really appreciate how you think about pre-existing structures and how those can become reactivated and really impact later structural geometry, as that's huge in the world of structural geology, and you do a nice job kind of like showing the importance of that and illustrating that, and it really resonated with me for a lot of the work that I've done in the Rockies.
Well, thank you. I think is important, and I just don't think, I'm not the first one that recognized this by any means. There've been a lot of people that have shown these features in papers in the past, Stone and other people. So I'm not taking credit for that, but I think I'm putting together maybe a better story of what happened and how we have crustal inheritance here, which people didn't talk about much in the past. But okay, so here's the map, just for quickly. Can you see that, Molly?
Yes, I can see it.
Okay, so this is the base map in Illustrator. I don't know for you that are familiar with Illustrator. It is similar to ArcGIS, but not nearly as complex. But anyway, I brought it all. So these layers are based on ArcGIS from the Montana Bureau. Comes right in Illustrator, and so here you can see the map. This is now the whole map. This is 56 100K maps. This is all of eastern Montana. So the Beartooth Mountains are down here, and then Powder River, Wilson Basin. So we'll talk about that. I'm going to zoom in a little bit, but I just wanted to show you how big this map is. And this area will be for explanation and showing the units, the strain ellipse, etc. And then I'll have a paper that goes with it. And then these are various units, faults, etc., and the geologic formations. And you can see I simplified this, so you can see in the light gray, as I showed earlier when I zoomed in, Cat Creek Fault Zone is right in through here, the wider zone. You can see the Lake Basin Zone, Fromberg. Those are all in the light gray that I've shown at least preliminarily right now. And the geology has been simplified, so you can see the Mesozoic rocks in green, etc. And so now let's zoom in on an area maybe that you've been before, and that you've seen and I talked about. So now we can go to that same place in the Power Mountains, and you can see the colors that I've broken up. And this is probably going to get the scrutiny of reviewers. I wasn't even sure I could even do this, but it does fit well. And then I can color these as based on the simple shear strain ellipse. And so that's my interpretation. But I think I can argue that it really does fit nicely with the simple shear strain ellipse. So this would be the Nye Bowler again coming through here. Fromberg fault zone now. This is, as I mentioned, all we can really see there is the trace of the master fault at the surface. Okay, I'm going to zoom out a little bit more. And so as we come up here, now you can see all the work that I've done since I did those first two maps. In the Lake Basin, we can see the normal fault zones very clearly with a few other faults going through there. Move up even farther, there's that Bull Mountains Basin that we talked about. And then we get into the Cat Creek zone. I'll zoom out a little bit more. See, it's a very wide zone, so I've identified two, I think, major synthetic faults that I had seen in similar as I seen in Wyoming that I added to that paper that I did on the Owl Creek zone. And so that would explain these normal faults that we see here coming off. So you really got two zones of normal faulting, and then a third zone down here, which explains these major curvilinear reverse S-shaped folds. So then we move in further to the north, we see the Weldon zone, and here's the dashed the Poplar Dome fault zone. So Poplar Dome is right in here. So I believe this zone was probably more continuous before, and that's why the Brockton-Froid goes more off to the northeast. And so just real quickly, you can, with these layers, this is all still, could be go back into GIS. You can turn these off and you see just the structure, which is kind of cool. Turn off the geologic units. Within the geologic units, I can click on various, and I left this stuff in there. So you can see the units, and it quickly clicks to whatever unit this is. That's going to be the KB. So you can show this, you can find these, you could put this back into ArcGIS, and it would still be geospatially correct. So that's the neat thing about that. And those are kind of the neat things that are still in this, and this could make perhaps be at some point some sort of a working map that people could work with rather than just be a hard copy type map. And so with that, I'll call it good.
Awesome. So thank you again. I still haven't seen any questions come through, so feel free to type them in quickly or raise your hand if you want to ask them out loud. I'm kind of looking forward to diving in more to some of the work you've done, and kind of just a general question. How much of this do you think really extends into the Williston Basin? Because that's a basin that I want to learn more about going forward. And I've worked the Powder, the DJ, all of the Rocky Basins, but I haven't gone as far east as the Williston yet.
Can you see that? Probably can't. Just a second here, real quick. Can you see the map still? Oh, wait a minute. Sorry.
Yeah, I can see the map still. Well, not now.
Okay, a second. Let me share again and go back to PowerPoint.
Then we did
Sorry.
have one question on that map. What's that big circular feature in central Montana?
Oh, off to the northwest? Oh,
I think so. I think it was pink, if I remember right.
yeah, that's the Bear Paw Mountains.
Okay.
So I think that's off. It's right at the boundary, though, I believe, of the Wyoming Craton. But from work I've seen, it would be up in. Are you seeing the?
I don't see your map anymore.
See the 1.8 GA event?
Um,
No.
you'll have to share
Wait a
your
minute.
screen.
Yeah,
Share
I bet you.
again and see if it comes up.
Sorry, I'm not finding the share screen. Here on the Zoom. Let's see. Oh, that's not it. Okay, sorry. There it is. All right. Oh. See it there?
Yeah, now I see it.
So that there is the Bear Paw. And so you can see how these faults all kind of come up. My interpretation is they're kind of coming up right to the edge of the boundary. And this over here would be the Great Falls tectonic zone in the basement. Okay, so you kind of don't see as you get further to the kind of the northwest here that these faults are extending any further. There's really no evidence other than Lake Basin, which all looks like it lines up with the Lewis and Clark as you go up into northwestern Montana, but I think that might just be coincidence.
Okay.
So, and then just real quick, sorry. So you mentioned North Dakota. So if you look, I have some publications on this. If you look at the North Dakota website,
Yeah.
I talk about what happened in North Dakota. I have a tectonic map. It's not a wrench fault tectonic map, but it does allude to what I think happened. Because now you have the Trans-Hudson, with this all closing up, you have the Superior Craton off to the east. I believe when this crashed, when the Superior Craton, when that closed up, it damaged the western part, or as my friends in Algeria say, there was an accident. But it fractured it, but it would have been more from the east-west. And so your conjugate shears are going to be more northeast, southwest, and northwest, southeast.
Okay.
But again, with that principal horizontal stress coming in roughly east-west, that's kind of what we see. And we see a lot of this stuff right here along the Cedar Creek extending. So these faults down here, they're all right lateral that are going to the northwest. They've been mapped as right lateral. And there's evidence for right lateral motion on the northwest trending basement rooted, or northeast trending, excuse me, basement rooted faults in North Dakota, in the western part. And that's why I call this the Western Dakota uplift. This is the area, it has been uplifted. And so you get the Badlands in here. And there's a reason why. It's because it's also, you see a pretty big thing crashing in here. And as this, can't remember the name of it, starts with the name, Manitowoc Ocean or something like that. As that closed up, you had the basement here being hit by the Superior prior or after 1.8. GA, about 1.6. I don't know exactly when, but somewhere in that ballpark. And that will, I think, help explain, but I still think you see during the Laramide that those faults were reactivated as right lateral strike slip faults, even into North Dakota.
Cool. Awesome. Yeah, thank you again. Yeah, as I've mentioned before, your work has always really been helpful for helping me wrap around some of the
Well,
stuff.
that's what you'd like to hear, that somebody can get something out of it, because that's the ultimate, kind of the ultimate goal. It makes me feel like my work is worth something. So
That always
I like
feels good.
the time to present, and I'm hoping to come up with some neat things with that lineament paper, as well as maybe even moving into Colorado, if you can believe that.
Yeah,
Laramide is in Colorado as well, and I think I can explain. I'll leave you a little carrot.
we'll do it. Do
This,
it.
with this model, because Colorado is different.
Okay. Yeah.
So I know
Awesome.
people that would say you're crazy, but
There's always those people.
I'll see if I get to it.
Do it.
All
Awesome.
right, thank you very much.
Yeah, thank you again. I really appreciate your time and all of the information. So appreciate it, Jeff.
Yeah, and if anybody wants to email me, they can contact you, and if they have questions later, no problem, I'll try to answer them, and I won't be so rushed. I was a little rushed. Fortunately, get going. Whenever I talk, it's longer.
That's okay.
But at least people got to see the map, so.
Yeah, that's true. All right. Well, thank you again and have a great afternoon.
Okay, thanks so much. I'll talk to you later.
All right. Bye.
Bye-bye.